Actually, let's do it now. We can do this calculation with this example here. So we have pith balls. How much mass do you think these pith balls have? Take a guess. 1 gram is a better guess. So this is 10 gram made out of metal. So something that's, pass it around please. So something, that size made out of styrofoam, 1 gram is probably a closer guess than anything else. It might even be smaller. So let's say these are 1 gram pith balls. And I want you to just imagine that the demonstration that I was trying to do worked, and that you could see a nice separation between the pith balls. This is where you just have to use your imagination because my demo didn't work. And let's say you get really large separation, larger than you could imagine happening here. Let's say it's separated by as much as 15 degrees. So that together it's about 30 degree separation. It's a pretty big angle. And I want to calculate how much charge should be here that would cause that much separation between them. Yeah? So how would you go about answering the question? How much charge should be here to get that separation? Have you learned any tools in previous physics classes that helps you tackle a problem like that? F equals ma. So what Seungmin, you are saying is that this problem involves forces, right? What strategy do you use with the force problems? Standard strategy. So that's why that's why we had that crash course in problem solving in physics, on the very first day, because we are going to come back to this. You're going to have a sense of forces. So yeah, this is a force problem, meaning you should go through a force problem strategy to actually work the answer out. So let's go through it quickly. It's not going to take that long. So we have, let's start out with the free body diagram. And I'm going to draw a free body diagram for one of the masses here, this mass here. So what are the forces on that mass? There's going to be gravity, mg pulling it down. Any other forces? There's the force from the string. We call that tension. That goes in the direction of the string. So tension. Any other forces? There's now one more force, electric force, that's going to be, so it's now another non-contact force you have. You know that these two separated due to electric repulsion. So there must be electric force pushing it that way. So that's something new that you are going to now have to enter by hand, electric force. All right. Does this look like a complete free body diagram? Yeah, no other forces that need to be there. All right, so what's the next step in the strategy? I drew a free body diagram.
Break down the forces.
We have to break down forces. Now, breaking down forces implies that we are talking about components, right? What do you need before you can talk about components? I mean, you are going to have to label the angle somewhere. But so when you're talking about components, you're talking about x and y components, right? Here, can you tell which direction x and y components go?
No, you haven't defined them.
You need the coordinate axis. So that's the second step. I mean, the standard strategy steps, it's supposed to be in a logical order. When you try to skip a step, you will realize that you haven't done something that was a prerequisite to the step that you're trying to do. So you are trying to break down forces into components. That's where you should realize, I don't have any access to talk about components of. So you should define axis. Here, it's simple enough to define this way. In physics 4a, we had you look at acceleration and try to define this along acceleration. Here, what's the direction of acceleration? Is there any acceleration? Yeah, it's static, zero acceleration. So this is good enough. So the components along x for the electric force is just all along x. Gravity is all along y. So it's only the tension that needs to be broken into two parts. So there's going to be tension along the x-axis and tension along the y-axis. Now this is the step where you might want to start drawing the theta that you are given. so that you can start expressing this in terms of theta and the tension. What is the x component of tension in terms of those known quantities? Could you say it louder? Yeah, t sine theta. It's the opposite side. So it's sine theta. And the y component is t cosine theta. It's the adjacent side. Okay. All right, what's the next step? I broke forces into components. Pedro, what's the next step?
Well, how we used to do it is just the force of this, the Fe, or force of the electric charge minus the t sine theta.
Wait, what? So you're trying to tell me what you would do. I want you to first to give the description of the step. What are we doing in the step?
We do the flow charge of the x and y.
Not charge, force, right?
Yeah.
So what does the net force relate to? Mass and
Area.
you are recalling the letter A, but it's not area.
Oh, acceleration.
Yeah, acceleration. Yeah. So we are writing down Newton's second law equations. So that's the very last step in standard. So if you feel rusty with the standard strategy, time to review this now, because as you will see in the homework problems, you're going to be asked to do more of those questions as you go. One question that will come up especially often as we do magnetism is a circular motion. So, if you didn't feel comfortable with those when we first covered it, time to review this now. Because, this is the aspect of physics that is cumulative. So we're going to write down the Newton's second law equations. Net force is equal to mass times acceleration. So hopefully with this you remember everything, that we have to do this, one for each object and one for each component. So here I'm going to write down two of them. So net force along the x direction and the net force along the y direction. So along the x direction, as Pedro was telling me, electric force minus this, Fe, I keep capital E, minus t sine theta. Here it would be mass times acceleration, but acceleration is 0. In this case, acceleration is 0, so I can say this is equal to 0. The y component is the y component of tension and gravity. So t cosine theta minus mg is equal to 0. Good. So we are still reviewing standard strategy. This is what the standard strategy leaves you at the very end of the steps. So what you should do at this point is count your equations, 1 and 2, and count your unknowns. Do you know tension force? You don't, so that's an unknown. Do you know angle theta? Yeah. Do you know the electric force? Yeah, I don't know that, so electric force is unknown. So anything else unknown here? Yeah, okay, so everything else is known, which means, I can solve this for electric force, and hopefully I can use that in this expression to find the charge Q, right? Like a distance is something I can figure out, right? Yeah, so let's solve this for electric force. So I'm going to try to eliminate tension. The way you do it, hopefully you are remembering all this algebra stuff. You first solve for tension and then plug it into the other equation. So solve this for tension. T is equal to mg over cosine theta. Plug it in up here. Then electric force is equal to, move this over, plug this in, mg sine over cosine or tangent theta. Good? So this is the expression for electric force, but that's not what I want. What I want is the charge. So I need to sort of copy this over. So say all of this is equal to k. That's a number I'm going to plug it in. And I have to start inserting some assumptions. If I simply wrote this as Q1 times Q2 over d squared, how many unknowns do I Can I solve for Q1 and Q2 separately? Not enough information here, right? So I'm going to make an assumption and say, well, maybe these are same amount of charge for both of them. They don't have to be, but I'm going to work it out for the case where they are. Okay, I need an expression for distance. You know what? Let's make it easy for ourselves. I'm just going to say, I'm just going to estimate, because that was the point of this exercise. When this distance, so this is about 15-degree angle. What does the distance look like between them? 10 centimeter, good enough of a guess? 10 centimeters? Okay. So, I mean, I can come up with a trigonometric expression for D, but I'm just going to say distance, I'm just going to say D is equal to 0.1 meter. Good. Because I'm kind of running out of time and I want to do other things too. So let me finish this problem. So I have this is equal to all of this. It's the charge, amount of charge I was interested in. So I'm going to solve for charge. The way I do it is I move everything else over. And since it will be q squared on one side, take the square root of q squared. Okay? So let me write down the version where I moved everything else over. So I have q squared is equal to d squared times mg tangent theta divided by k. Right? So for the value of the charge, it's a square root of all of this. And you know I don't like to plug in numbers, but this is one exception I'm going to make and actually plug in numbers, because this is one case where I think the number is it's illustrative. It illustrates. It gives you some sense of what is a physically reasonable amount of charge Q. So if you have a calculator, please do it on calculator, but let me do it here on, let me demonstrate how to do this on Wolfram Alpha. wolframalpha.com. So Wolfram Alpha is one of the advantages of Wolfram Alpha over your handheld calculator is that Wolfram Alpha is aware of units. It's also aware of physical constant. So I can actually do it this way. So for the charge, it's going to be square root of distance. I said it at 0.1 meters times mass of 1 gram times g. Can I just say g? Let me just say 9.8 meter per second squared times tangent of one downside of Wolfram Alpha is, I don't know if we can, let me try 15 degrees. Okay, all of this divided by k. And I don't think Wolfram Alpha knows k, so I'm going to write it this way. 1 over 4 times pi times electric constant. That's Wolfram Alpha's name for epsilon naught. Yeah?
The 0.1 meters shouldn't be squared.
Oh, thank you. I forgot to. Yeah, 0.1 meter square. Yeah. Good? Any other mistakes? No? Okay, let's see how. So Wolfram Alpha will tell you how it interpreted my request. Make sure it actually makes sense. 0.1 meter squared times 1 gram times gravitational thing, a tangent of 15 degrees over 4 pi epsilon naught. All right? Ampere second. Ampere is a unit that you will learn later. That's a unit of current. Coulombs per second. So ampere second is charge coulombs. So Wolfram Alpha, by the way, did all the implicit unit conversion, like from grams to kilograms. That's one of the things that's nice about Wolfram Alpha. So when you plug in all the numbers, or do it carefully on your calculator, when you're done, this is the number you get. 5 times 10 to the minus 8 coulombs.